Long before there were planets, there was only a disk. A flattened cloud of gas and dust spinning slowly around a newborn star, thin as a coin held at arm's length against the dark. Everything that would ever exist in this system was still inside that disk, unformed, unnamed, and already turning in the same direction, on the same flat plane, at the same stubborn tilt. Dust clumped into pebbles, pebbles into boulders, boulders into worlds, and every single one of them, from the smallest moon to the largest gas giant, was born already spinning with the disk that made it, carrying its motion like an inheritance no one had the choice to refuse. That disk is called the ecliptic, and the system it built is ours. This is the story of the one direction nothing born here was ever built to travel, and the one machine that tried anyway. Every planet orbits the sun in almost the same plane, tilted from each other by only a few degrees. Mercury drifts closest, tearing around the sun at roughly 47.4 kilometers a second. Neptune drifts farthest at a lazy 5.4. And between them, Earth carries a number worth remembering. Roughly 29.8 kilometers every second, sideways, forever, the residue of the spin the disk gave it some 4.6 billion years ago. Even the debris left over from that construction settled the same way. The asteroid belt between Mars and Jupiter clusters close to that same shallow plane, most of its members within a few tens of degrees of it. The disk did not just build the planets. It built the geometry everything afterward would be measured against. That sideways motion is not incidental. It is angular momentum, conserved since the disk first began to collapse, and nothing born from it is exempt. A spacecraft launched from Earth does not start from zero. It starts already moving at 29.8 kilometers a second, whether it asked to or not, because it was assembled from parts forged on a planet that inherited that speed at birth and carries it out of the launch pad by default. Go outward, and that inheritance works for you. Go upward, straight out of the plane, perpendicular to everything the disk ever built, and it works against you in full. Here is the arithmetic no launch brochure advertises. To leave the solar system entirely, a spacecraft near Earth's orbit needs to reach roughly 42.1 kilometers a second relative to the Sun. Earth already hands it 29.8 of those for free just by launching prograde in the direction the planet is already moving. The remaining gap, a little over 12 kilometers a second, is closed the clever way, not the expensive way. Jupiter, and sometimes Saturn, lend a spacecraft their own orbital momentum in a maneuver called a gravity assist, a slingshot that costs almost no fuel at all. This is precisely how Voyager 1 and Voyager 2 left the solar system in the late 1970s and 1980s, and how Pioneer 10 and Pioneer 11 managed it before them, all four riding the plane outward, spending the inheritance instead of fighting it. Now flip the direction. To leave the plane instead of the disk's radius, to go up perpendicular to the ecliptic, the 29.8 kilometers a second sideways cannot be spent toward escape. It has to be canceled first before a single meter of upward progress is made. Canceling a velocity costs exactly as much delta V as the velocity itself, nearly 30 kilometers a second, spent purely on undoing momentum before the spacecraft has gone anywhere at all. Only after that debt is paid does up even begin. Compare the bill. Roughly 12 kilometers a second to leave the solar system outward, riding the disk's own motion, against nearly 30 to leave it upward, fighting that motion the entire way. Up is not merely harder. It is, by the numbers, the single most expensive direction in the solar system, more expensive than leaving it altogether. Picture a record spinning on a turntable and a marble resting at its outer edge. The marble did not choose to move, the plate is moving, and friction drags the marble along with it, around and around, at whatever speed the plate has settled into. Now try to lift that marble straight up, off the plate, without letting the turntable's spin come along for the ride. It cannot be done gently. The marble is already traveling sideways at the plate's full speed the instant it leaves the surface, and any attempt to rise straight up first has to cancel that sideways motion, Or the marble simply arcs outward, still carried by the spin, never rising cleanly at all. Every planet, moon, and spacecraft assembled from solar system material is that marble. The plate is the ecliptic, and no one has ever found a way to lift the marble without first paying for the spin. Only one spacecraft in the history of spaceflight has ever paid that bill in full. Its name was Ulysses, a joint mission of the European Space Agency and NASA, launched on October 6, 1990, aboard the Space Shuttle Discovery. Its destination was never a planet. It was an angle. Ulysses flew first to Jupiter, arriving in February 1992, not to study the giant planet itself, but to borrow its gravity the way Voyager had, except in reverse. Instead of using Jupiter's pull to gain speed outward, Ulysses used the flyby on February 8th to bend its path sideways, out of the ecliptic entirely, until its orbit around the Sun settled at roughly 80 degrees to the plane every other spacecraft had ever flown in. For the first time, something built by human hands was traveling the direction the marble was never supposed to go. Its new orbit swung it from about 1.3 astronomical units at closest approach to the Sun out to roughly 5.4 at its farthest. But the distance was never the point. The tilt was. What Ulysses found, flying now almost directly over the Sun's poles, was a solar wind behaving nothing like the models built from equatorial data alone. Faster, more turbulent, structured in ways the in-plane missions before it had never been positioned to see. It kept flying that polar route for nearly 2 decades, completing 3 full passes over the Sun's poles, 1994 and 1995, then 2000 and 2001, then again in 2007 and 2008 before the mission finally ended in 2009. And through every one of those years, Ulysses never carried a camera. Every gram and every watt of its payload had already been spent on the instruments that made the climb worth taking: a magnetometer, solar wind plasma analyzers, cosmic ray detectors, interplanetary dust counters, machines built to feel the Sun's poles, not to photograph them. No one had budgeted for a lens, because no mission had ever needed one at that angle before. Other spacecraft have looked back at home before. Voyager 1 turned its camera around in 1990 and captured Earth as a pale blue dot. Apollo astronauts framed an Earthrise over the lunar horizon decades earlier. Both were taken from deep inside the plane. Every iconic photograph of this solar system, however far the lens traveled, was shot from within the same shallow disk the marble has always spun in. So somewhere in every textbook, every documentary, every diagram of the solar system drawn as a flat disk of neat concentric rings, that image is not a photograph. It has never been one. It is a reconstruction, a model, an illustration built from data gathered almost entirely from within the plane itself, because the plane is the only place anything human has ever been able to afford to stand. The one machine that ever climbed high enough to look down on the disk instead of across it was busy measuring a wind no one had felt before, and had nothing left over to point a lens at the view it alone had earned. That is the real shape of the word up out here. Not a direction blocked by distance, but one blocked by debt, a bill written into every object the disk ever built, payable only in the exact speed it once gave away for free. Ulysses paid that bill once and came back with a wind, not a picture. Maybe one day something climbs up there again, instruments this time built to look as well as to feel. Until then, the view stays unclaimed. Let's keep watching until someone finally takes it.